On the quiz, you already saw the difference between vectors and scalar. Now, what you might not know about this is that all the math you ever learned in your life, it was all scalar math. Think about it. All of it is just multiplying numbers together, even calculus, pre-calculus, whatever math you got to, right? It's just multiplying numbers together. All that math that you've learned can be done with vectors. So think of it as your entire life so far, you've learned math with numbers, right? But there's an entire other field of math, another layer of math, so to speak, where numbers also have direction. Are you with me, I'm saying? And then there's actually another field above that, where in addition to direction, you can have another layer on top of it. It's called tensors, all right? What I'm trying to say is that you have no idea, but there's an entire field of math that goes beyond numbers, right? Today we're only going to talk about simple things like adding vectors and subtracting vectors. Later in the year we might bring in something called a dot product, which is a new kind of operation that you have not learned about. It's kind of like multiplication, but not really. And then there's a cross product, kind of like multiplication, but not really. So there's a whole other layer of math that is extended in the realm of numbers. In physics this matters a lot because physics is trying to describe the way things work. And when I say I'm going at 5 miles an hour, that's great. But it doesn't really tell me where I'm going. Right? So if I'm going to say I'm going 5 miles an hour that way, now I have a vector. Right? That's the difference between them. Yes?
Teacher and students, pardon the interruption. Students, any student that has a completed package for Matter Virtual, we are asking that you please come to the office at this time.
Anybody doing that? Here?
Again, any
Alright,
student
so
that has a completed
continuing
package
this.
for Matter
So
Academy,
let's review the ones we get on the quiz.
the office.
Vector or scalar, you can sing it out loud together. Please do that. Everybody, let's practice this, okay? Velocity. What is it? That was fail. Vector or scalar? Velocity. Time. Mass. Right, because does it make sense to put direction to mass? Right? Alright, well, what about speed? Scalar, doesn't have direction. How about displacement? Force. Does that make sense for force to have direction?
Yeah.
Absolutely. How come energy doesn't have direction? Because it's just what? Does it make sense for, energy is that way? Energy is like a quantity that you have. Are you what I'm trying to say? The quantity you have. So that's why. How about acceleration? Vector, very good. Alright, so make sure we review those. What is the difference then between a scalar and a vector? Vector has direction. Okay, so that's the first thing I want to talk about. The next thing I want to talk about is that there's certain things you can do with vectors. For example, you can split them. So a vector like this can't be split in terms of x and y components because it only has a y component while it's fully straight up, right? Only has one component. Or a vector like this only has an x component, so it can be split up, right? But when a vector is kind of like at an angle, right, with our reference frame, right? Although if I twist this could be an angle, depending on the reference frame. But if the reference frame is the board, that one has an angle with the horizontal, right? And we can split that into two directions, and we call that direction the y direction. So like let's call this vector a. So that would be ay, and that would be ax. Now we just split them using trig, right? Now, because I have this angle, not that angle, this is cosine and that's sine. Why? Because in trig, what do we call cosine of an angle? Adjacent, which will be the ax, over hypotenuse, which will be the a. Which means if you're solving for ax will be a times cosine of theta like we saw in the quiz. Right? If you're solving for ay would be using the sine. Why? Because the sine of theta would be equals to ay over a, which equals, so that means ay could also be called a sine of theta. Now don't memorize that the y is always sine and the x is always cosine. It depends on the angle you give. If I knew that angle instead, then that's cosine and that's sine. Are you with me? Because it's the adjacent and hypotenuse. Alright, so you gotta be careful. You gotta make sure that the angle they give you, if the give was with the horizontal, then the x is the cosine. Are you with me? Which is usually what I do a lot of cases. By the way, you can also set up a relationship using tangent, right? You can also set up a relationship using tangent. That's how you set up a relationship between the components. So if you ever need a problem that you need to set up a relationship between the components, you can do that. It will be opposite, which will be AY, over adjacent, which will be AX. Alright? Now you can do that as well. Now, that's how you split a vector. Right? So how do you put a vector together, the opposite of it? Right? So that would be, how would you get two components? Right? Remember, this is why you split. Now, if you don't have this kind of stuff in your notes, you should add it to your notes. That's why you have the Bowringer thing. Alright? If you don't have this in your notes, like seriously, put this in your notes. Now, this is a split components. Let's talk about adding components now. Now, if I have a vector in the y direction, I'm trying to stay consistent with the color in here. This is why I asked for different color pens, so you can do the same on your notes. So if I have something like this, right, and something like that, AX, and of course these things could be numbers that I'm putting together, they have a value, right? And I want to try to figure out what the resultant is here, my A, and of course these are vectors. What I'm actually trying to do is a vector addition problem like this, where A equals AX plus AY. Now, how do I do that? How do I add these things together? Right? Because you don't just add the numbers because they have directions. Right? So the right way to do it is to do a Pythagorean theorem here. Right? So you're going to do A equals the square root of AX squared plus AY squared. Right? But that will give you only the value of A. So how do you get the actual angle of it? You're going to need that. Are you with me? So what you do, if I'm trying to solve for the angle, I have to do the inverse stand on the opposite side. So the angle comes from the tangent inverse of the opposite, which in this case, if I have this angle here, the opposite will be AY over the adjacent. Now notice what I'm getting when I'm doing this. That's very important. This angle is what angle? Is the angle that calls y opposite and x adjacent. Because you're going to make sure which angle you solve for. Are you with me? Because if I put ax over ay, it's like I'm getting that angle there, not this angle here. No, you have to give them a direction. So which direction is this vector going? Right? I could say it's going this many degrees above the horizontal. Right? But I could also say it's going, use the other angle to give a direction to it. It depends on your reference frame. Are you with me? But either way, that's how you add a component. So we talk about splitting components, we talk about adding components. Is that cool? Alright. So then, we're going to start doing now this thing, and we'll work on it together, and we'll see, as we're going through it, there will be a lot of the different questions that we have to address. We're just going to use this and some other skills that we have to look at. Actually, before I do that, let me show you something else about simple addition and subtracting of vectors. Alright? So if I do A, this is a vector A, which is this vector. And then I have a vector B, which is this vector. Right? And then I have a vector C, which is that. That's C. Right? So if I do A plus B, this is vector addition we're doing. Right? Because they are both only x direction vectors. How do I add them? The general rule about adding vectors is that you move the tail of one to the head of the other, and then you add it, and that's your result. So it will literally be putting the first one, putting the second one, and then the resultant, all right, A plus B, would just be that. Are you with me? So because they are in the same direction, they will all obviously add in the same direction, so you say they're going to the right, and there will be the total value of both of them combined. So it just looks like a normal addition problem. So if this was 3, so let's actually put numbers so that it makes sense. If this was 4, that was 3, and this was 1, right? This would be 7 to the right. Notice if I just say 7, it's not a vector, right? I have to say 7 to the right, right? Now, what if I was doing A plus C, right? Now, the rule is still the same. You put the tail of the first one, and then you put the head of the first one on the tail of the second one, so it will be here. Right? And you can see how C is subtracting out of A. Correct? So that means it will be 4 minus 1. Right? Which will be, now notice that when you're working with the value of the vector, things to the right are positive, things to the left have to be negative then. If you say things to the right are positive. If you say up is positive, bottom has to be negative. Are you following what I'm trying to say? Alright, so then this would have to be 4 and 1, but 1 negative, because it's the opposite direction. Just like we do with velocity. So this would be 3 to the left, to the right, 3 to the right. Are you with me? Now, what if I was doing subtraction? A minus B. Right? Now, when we do 4 minus 4, right, what we're actually doing is doing 4 and adding to that negative 4. Are you with me? So what is B? Negative. The opposite of B. So you literally flip the vector. So there would be 4, and then you follow the rule, you put the head of the one, with the tail of the other. But this time, your vector has literally to be negative B. So that means I have to put negative B over here, right? So I'll have a vector A that's 4, and a vector negative B that's negative 3. My answer would be 1 to the right. Right? Would be my little answer. Are you with me what I'm saying? This would be 3 to the left. Right? To the right, sorry. Now, that's all fun and games and easy, but what if I have a third vector, D, that is vertical, like this. And let's say I call that vector also 3. And now, let's say I'm doing A plus D. A plus D. Now, wouldn't that just be, now by the rules I have to put the tail of one to the head of the other. So then, that's exactly what I would do. I'll put the A plus D. Right? And that's 4, and that's 3. Now, isn't that, then my solution is I connect the head of one to the tail of the other, right? So my resultant would be this. Right? And I will do that. I'm back over there. Are you with me? So those are easy. What if I have a less vector, vector E, that is like this? All right? So, and I'm going to give you an angle here. I'm going to say this is 30 degrees. All right? And this is a value of 4. Okay? And now I want to add that vector to A. Okay? So I'm going to do A plus E this time. Right? Well, the rule says I can do this graphically. I have to put a 4, then connect the head of the one to the tail of the other, so I have to put the other one here. Right? Just like that. So that's 4, and that's also my 4, not to scale, right? So my resultant would be here. If I did this to scale using graphing paper and stuff, and a ruler and stuff, I can measure that and use proportion to figure out the actual size of it. Right? That's the easy way to do it. The hard way to do it is that, how do I add this to this? Geometrically. There's actually something you can do, it's called the law of cosines, which is very easy. But without teaching you that, there's an easier way even. You can think of this 4 as those splits components. Are you with me? So then you get the 4, and you turn that 4 into into an EX and into a EY. Are you with me? So you're going to split it the way we thought about. And then you add the X part of this and the X part of that together, right? And you get a total X. Then you add the Y part of this and the Y part of that together, and you get a total Y. Are you with me? Now you have a total X and a total Y, and you combine it that way. I'm going to do a problem like that for you guys in a second. That's the last way of adding vectors that I have to talk about. Now, if anything was subtraction, let's say I was doing this, A minus E, all we have to do is do what with the E? Literally flip it so that E will go back down. Is that clear? All right, so then let's go over this really quick, and then I will talk about the activity for next time if we have time. All right? Now, find the hypotenuse in a smaller angle in a right triangle whose known sides are 56 and 64 centimeters long. So, have anyone done this yet? All right? Are you going to do this to the board for us, please? Just come up here and put it on the right side. Okay, get a piece of chalk, do it. How about number 2? Let me see what number 2 is. After he's done it, we'll see if it's right. Now, we already did number 2, didn't we? What is the difference between a vector and a scalar, Lebardo? Lebardo's asleep, loses the point. 1, what's the difference between a vector and a scalar? Yes?
Vector.
Yes?
Back to me. Vector has direction.
Stop stealing his question.
That was my question.
Yeah, but you were asleep.
No, because I didn't have the tab to see what.
Who cares? I asked you the question. You don't need to look at it. Alright? So yes, it is. Okay, so it's a
Vector has direction.
vector has direction. Give 3 examples of each in physics. We already did that. Make sure you do that in the question. Now, number 2. How do you find the x and y components of the vector on the board? We did that already also. Didn't we? The whole splitting the vector x and y components. Next one. How would you find the resultant of the components? We did that, correct? By adding Pythagorean theorem. So we already did that before as well. Can a vector component be big? Oh, now it's a conceptual question. So let's think about this. Elizabeth, where are you? Right here? So I'm saying, can a vector component be bigger than the resultant vector magnitude? Yeah, can you have a vector? Now, when we are talking about component, we are talking about x and y components of a resultant vector. So if I have this, right? So they're saying, can a component, ay, ax, can a component that makes up the resultant be bigger than the resultant? What do you think? Think about different setups for that.
That's what I was thinking. Like, I'm thinking, what if it's negative? And then.
What about rules of triangles? The result is always what? Can a component be bigger than the result?
No.
Geometry. So you have to think about it and stuff, but eventually you go back to geometry and you think about the hypotenuse. By definition, the hypotenuse is always what? The longest side. Are you with me? So that doesn't make sense. Now, can you somehow have a vector that has non-zero components? Alright? That's it. Can a non-zero vector of different magnitude, okay, sorry. Can vectors which are non-zero add up to 0? Can vectors of different magnitude add up to 0? Is there any way to make that happen? 2 vectors that have different magnitude add up to 0. So how do we do that? To add up to 0, the easiest way to think about it is if you have one and subtract the other. So if you got 4 and 3, for example, that's not going to work, right? But is there any way to make a triangle then, perhaps, that would make that work? Can vectors of different magnitude cancel each other out, is the question asked. Can 2 non-zero vectors of different magnitudes cancel each other out? Of course not. Could you do it with 3, though?
Yes.
With 3 you could. Because now I could have something like this and something like that, right? And they're both adding together, so I can have that. And then I have this as my result, right? So that means if I get a vector that's like that, the opposite of that, and add to those, it would have canceled that out. That's actually a very important thing. It's just called the equilibrium. I'll show you again, slow, because I get a bit confused. All right, let me show you again. If I did this vector, and then another vector, like that, right? And I connect it. That's the result, correct? If I have a third vector, that is the opposite of the result between those two. This one. Are you with me? And I had added that one to those two. So what that means? I would have to get this and put over there. What would be my result? 0. So the equilibrium is the opposite of the resultant, which would basically, if I add the equilibrium to those 2 vectors, it will make the result 0. That's what the equilibrium means. How do you find the equilibrium? You find the resultant and do what to it? You flip it. Are you with me? Very important question. Alright? Yes? It is a master physics. That master physics thing is actually really good. Alright? Now, we already did this thing. Alright? If adding a vector A to a vector B to get a vector C, what has the orientation between these 2 things be? Right? So if I have a squared plus b squared equals c squared, what does that mean about the orientation of the 2 vectors, a and b? They must be what to each other? They must be what? They're by right triangle. That's why, because what you're doing there is some sort of a Pythagorean theorem thing, right? Now, if you're doing a plus b to get c, that means a and b are probably what? Pointing in the same direction. But if a minus b equals c, that means a and b must be what? Pointing in the opposite directions. Okay, good. What is the meaning of subtracting a vector? To flip it and add it. Are you with me? Very good. Give it Jennifer legal. Now, This is awesome. If rain falls down, how should you hold the umbrella while you're walking to keep the driest? Explain using vectors. Okay, rain is falling down, right? But you are walking in the rain. No way. It's falling down. You are walking in the rain. What is the best way to hold the umbrella? But you have to use the vectors to explain. All right? You got it, Barbara? Gonna try?
You hold your umbrella.
No, you know what the answer is. Because you have no, you hold the umbrella up? That's wrong.
You said there's no wind.
Yes? Doesn't matter. Yes?
If the rain is going southeast, you hold the umbrella northeast.
Okay, none of that. The problem that we're talking about is simpler than that. We're talking about rain is falling down, you're walking forward. How do you hold the umbrella? You need to know the side of the angle, and you figure it out. Because look at this. If, this is a bit of route of motion. If
I'm thinking
the
A is
rain
right,
is falling
I'm thinking
down,
B is wrong, and I'm thinking
and you are walking right, it will actually feel as if the rain is falling that way, which means you have to compensate. Are you with me? Well, obviously forward. Right? The rain is falling that way, so you got to do the equilibrium and do the opposite, right? And fall against the rain. Are you with me? So if you are walking forward and you hold the umbrella like this, what's going to happen? The rain will hit you as you walk into it. But if the umbrella is forward with a speed that matches, now the faster you move, what do you have to do with the umbrella? The more you have to tilt it forward. Because why? Because the faster you move, the bigger this is, which means the bigger the angle has to be to create the hypotenuse. Are you what I'm saying? Does that make sense?
for which one?
Very cool. All right.
M.
If an object, okay, so now it's that final problem. But, actually, first there's 11. Why does wind feel stronger when you are sailing against it? So I'm going against the wind, and the wind is going against me. Why does that make the wind feel the strongest? Because in a way, it's my vector minus their vector, right? But what is, so that one minus the other, it adds together. Are you with me? What I'm trying to say. Think of it that way. The last one is a bit hard, but before we do the last one, let me see, we have 10 minutes? We have time to do it. All right, so let's do it. Last one is a math problem that teaches you how to do this vector business. Oh, wait, maybe this work. No way! No point for doing it again, Abby. Sorry. That's why I forgot about you. Go ahead, do it again, please. It was right? Okay. Did you guys see how this worked? No. If you did, come on, Abby, do it again. Alright, while Edric works on that, okay, I'm going to talk about how to do this problem. Now look at that. We have two vectors that give to us. One travels 50 meters, 30 north of east. Now, we have to translate that stuff. 30 north of east. So what does that mean to be north of east? Like that. Okay? East is to the right, right? So north of east means what? So what would it mean if it was 30 south of west? You would start from west and go 30 towards the south. What if I said it was 15 degrees east of north? What would that mean? You start from north and go 15 degrees towards the east. So you see, that's a way to give you a reference so when you start measuring the vector from. So 30, they're saying that there's a vector that is how much? 30 degrees? Alright, so you have a vector that's 30 degrees, right, north of east. Right? Does that make sense? And it's 50 meters. Okay? And then you have another vector that is 400 meters, 75 north of west. What does that mean? I start from west and I go what? 75 north. So I have another vector like this, right? That's probably like that because it's north. This angle here is 75 degrees, right? So almost 90 north of west. And then it's a bigger vector too because it's what? 400 meters. Almost 8 times that vector. Not drawn to scale, right? Not to scale. Not to scale. By the way, you can do these things to scale in graph paper and then measure and actually get the right answer. So if I wanted to say, All right, how far from the starting point this person went? This person went this way and then that way. So the displacement vector will be connecting this starting point to the final point. Now, notice this is not to scale. If it was to scale, it would be something like this, right? Right? And then the other one would have to be 8 times that size this way, right? Something like that. Are you with me? And then you would have that be your resultant vector. You could do this carefully. Now, on the graph paper, you call 50 2 centimeters. And then, of course, the other one would have to be 16 centimeters. And you measure a protractor. Are you with me? And then you measure the resultant with a ruler, and you will get exactly the right value. And remember that, let's say, for example, your value was 20, but every 20 is 2. You divide by 2. You figure out a ratio, and you figure out this. So you can graphically add this. And the activity for next time is one of the things you have to do. Right? But, which I'll talk about in a second. But, how do you do this mathematically? All right? Which is the harder part. The graphical part is just doing it carefully. Measure the angle carefully, draw it to scale carefully. And then draw the other one to the head of it carefully, right? And then measure your resultant carefully. But how do you do this mathematically? So together, they're both kind of weird angles. So the only way to do this simply is to split them. So for each vector, we're going to do that. We're going to get this vector here, we'll call it vector A, and we're going to get the AX for that. And we're going to get this vector here, and we're going to get the AX for it as well. But I'll call it BX, since it's a different vector. All right, so this is my vector B. I'm also going to get the same thing, but in the other direction. So I'll get AY for this vector. And then I'll get, what's the color? Purple. And then I'm going to use BY for this direction. So how do I do that? I split it by components, which is the first thing I taught you today, right? How do you split components? So let's do it. Actually, let's mathematically do it. So let's start with the AX. AX equals A times the cosine of the angle. And therefore, it's just going to be 50 times the cosine of 30. Cosine of 30 is that half? Thought? Or is that square root of, I don't know. Yeah? Somebody figure that out there. 25 times the square root of 2, 1.4. 25, 40%, each. It's like 33 or something. Huh?
35.4.
All right. 35.4 meters. Now, let's pretend we have 2 sig things, okay? So we have 35 meters, all right? But I'll leave that because we're going to need it in a second, okay? So let's do BX. BX is the same principle, all right? You're going to go to B times the cosine of the angle, right? So B is going to be 400, and the cosine of the angle, what is the angle? 75. So what do we get? Sorry? 100 what? What? 103.5. Now,
He says no. She got like 300 something. She got like 100.
it should be small, like 100, because this angle is only 25, it's 75 degrees. So think about it, guys. If I'm going 75 degrees, what's the size of this component? It's not very big. Are you with me? It's not very big. So, check please. Does not trust one person. Let's have more one person check. But anyways, what I'm trying to say here, let's think about this number though. If this is AX is to the right and BX is to the left, does it make sense to make BX and AX the same sign? BX should be what? Negative. Unless I call this side positive. Are you with me there? Right? That you have to manually think about. The only way to not have to manually think about is to transform this angle in terms of the same direction as that angle. And therefore, that would not be 75 at all. It would be something completely different. It would actually be 90 plus 25. Are you with me what I'm trying to say? Or 15. 90, which will be 105. If you do cosine of 105, you're going to get a negative number. You're still going to get a negative result. So there's 2 ways of doing it. You just think about it. It's left, it's right, positive, negative. Or you transform the angle. But that takes an extra math step. So I just look at the direction. It's going left. I want to put a negative sign. Is that clear? Wow. For the AY. Yes.
That 35.4.
It's wrong?
Yeah.
43.3.
43.3.
Okay, thank you. See, this is why we check. 43.3 meters. All right, so AY. AY has to be A times the sine of the angle in this example because the angle they gave us, the Y is the opposite, so you use the sine. So it should be 50 times the sine of 30, that is half, which should be 25 meters. right? Okay, which means by now, by would be b times the sine of the angle, or therefore 400 times the sine of 75. Somebody give me the number. It's going to be positive because it's going up, right? So what do we get? 400 sine of 75. Come on, people.
Yeah, 5 minutes.
I know. This way. So, what do we get? 400 sine of 75. What do we get? It's not negative.
Yeah, it's positive.
There's something wrong.
It's in the second quadrant, so that's
It's in the first quadrant.
No.
It's 75.
It's going that way?
Sine of 75.
Oh, no.
386.3.
Make sure you're not in radian mode when you're doing this, on your calculator. You have to be in degree mode. That's probably what happened with you. Degree mode.
I know.
That's what's happening here with the different numbers. You gotta be in degree mode. So what do we got? 400 times sine of 75. What do you got? 386.3 meters. Okay. So how do we do this now?
But when we
Now,
saw this,
to
I
get
think
our
it's-
resultant vector, what we're actually trying to do is we're trying to get A plus B, correct? To get our result, let's call it C. Alright? That's what we're trying to do. So that's what we're going to do, but per direction. We're going to do that per direction. So that means we're going to do AX plus BX to get CX. Right? Let's do that one first. What's AX? 43.3. What's BX? Minus 103.5. What do we get? Let's go. This in my head. Let's go. Yes.
Negative 59.7.
-59.7 meters. Right? Okay. Now we do the same thing for the y direction, right? So for the y direction, we have to do bx plus ax to get the cx. Oh, y direction. Bx, ay to get the cy. So what is our by? 386.4. What is our ay? 25. What is the total cy? What? 411.4 meters. By the way, this is Adrich's problem. If I have these two sides, look at the hypotenuse, I just do Pythagorean theorem. But now that I have the Pythagorean theorem and the thing, I can use cosine, tangent, or inverse sine, whatever I want to figure out the angle.
Wait, did I
Correct? So it's done correctly over here. Yes.
How come I got negative 60?
Radian mode, degree mode.
It's in different.
Okay, so I'll figure it out later.
Because the bigger number's negative.
This,
No, that right there.
that one,
Yeah.
it's 43.3 minus
The
103.5.
bigger number's
Yeah,
negative.
So it's wrong?
Negative 60.2.
60.2?
Negative.
Negative, you're right. Negative 60.2.
She gets
Now, hold on. Hold on.
There they go.
This is right, by the way, okay? We are almost there. The last step, since we have x and y now, we have our x and our y. We got to figure out this, right? So we got to do exactly the same thing, kind of, for that, right? So what do? Okay, we do 60.2 squared plus 4, doesn't matter because it's going to get squared, or 11.4 squared. Take the square root of that, we'll get our value for the vector, how big it is, all right? As far as the angle, we can do the tangent inverse of the opposite, which is the y direction, right? If I do that, then I'm going to get this angle, right, with the y direction. Opposite would be 411.4 over adjacent, which is 60.2, and I'll get the angle. That's how you do it. You split the vectors up at each direction separately, and then once you have each direction, you do the Pythagorean theorem, and then once you have the Pythagorean theorem solved, you do the inverse tangent to get the angle. Now, hold on. Next class, this is what you need to do. Pay attention. Those of you who passed the quiz especially, one of the activities that I'm suggesting this time to practice vectors, get a graph paper and create in this graph paper, right? Flashcards this big with 4 vectors in it. Only one of them can have only x or y. For example, you can have one that is just ax or just ay. All the other ones have to be some sort of in between this. Are you with me? So what you do, pay attention right now. So you're going to do, you draw 4 vectors. Maybe one is like this, one is like that, one is like that. Change the size, change the angle on the graph paper. Are you with me? Draw 4 vectors. You're going to have to give me the size of the vector and the angle that you drew it in. Are you with me? Bring that done, and then we're going to do activity with that. Okay, next time. If you choose to do that, you're going to do activity with it. I'll see you next time.